Yes, NMR videos. I think 4 videos have been posted, I believe 4, yeah. I'll post another one today on carbon NMR. You have a handout. 1 stack, white handout on epoxides. Some of you in lab today will meet upstairs at, we'll begin at 2:30 for check-in. Instructions in your lab manual for check-in. And then we'll have lecture time afterwards downstairs. Chemistry of alcohols and ethers. Continuing on. We did this one in class. How do we do on the next one here? Same alcohol, calcium chloride pyridine, followed by potassium cyanide. Cyanide is a nucleophile product here. Product, yeah? How does that compare to the product above? Enantiomers, yeah? Okay, we got good. Why this stereochemistry? Tosyl chloride. What does that do here? Going to make tosylate? Yeah? Tosylate would be yeah? And importantly, there's no change in stereochemistry when you make your tosylate because we're not doing any chemistry with that carbon there. The oxygen's reacting with the tosyl chloride. Okay, no change here. No change. But here, when we do the cyanide, potassium cyanide, and do the SN2, we just get 1 inversion and not 2. So understand your stereochemistry with these 2 approaches to making, both made a cyanide, alkyl cyanide, or a nitrile compound, but you're going to have different stereochemical outcomes, yeah? Below, alcohols with HF. What type of product we're making? Well, obviously we're under dehydration of alcohols, but when you're on a final exam or something, you don't have headings there. What are we doing here? Alcohols, HF. Okay, you got this. What's possible reaction here? There are certain transformations in organic chemistry you just have to know. Dehydration of an alcohol with strong acid, but an acid in which the anion is not going to do anything. And we know sulfate won't, phosphate won't, but I've also told you several times, F- will not. Other halogens will. Product here. Somebody got it?
Elimination.
Nick?
It burnates the alcohol. It's an elimination reaction with Hoffman.
Uh-huh. Can you name your product? Can anybody name their product?
Off the top of my head.
You have structure?
Yes.
Can you name it? You should be able to name the structure. Anybody? 1-methylcyclohexene. Yes.
And then you have to put like
Do what?
E1-cyclohexene.
I can't.
E1-methylcyclohexene.
E? Well, E implies that you can have a Z.
Oh, okay.
Can you have a Z? And by the way, it's not E if you strictly did it because high priority groups are all
It's
the same side. Okay, but you wouldn't call it Z because there's no E. It's not relevant there. You can't have that alkene is not stereogenic. You know the term stereogenic? Okay, not stereogenic. There is no E or Z. Okay. Seitzef. Say Hoffman or Zaitsev?
So it's not
Okay.
bad.
Zaitsev, more substituted. Okay, thermodynamic product. Mechanism is what? E1. E1 always gives the most stable alkene you can show. Okay? A little bit of heat. Heat favors elimination typically, yeah? We also have one over here. We're going to have double bond here. Benzene ring is a phenyl substituent, and doom. This alkene is stereogenic, and it will be E.
You have the double bond there, so you have conjugate, like same conjugate pi system.
Exactly. Pi bond, the alkene conjugated with the benzene ring is more favorable. Okay. You could argue either side is a disubstituted alkene. Okay. Putting the double bond on this side, beta hydrogen removed here versus here. Not as stable as that alkene. That one's conjugated here. This is not conjugated with the benzene ring because you have the sp3 carbon between them. Again, E1. E1 never gives Hoffman product, right? The way you're going to get a Hoffman product is doing E2. E2 requires strong base. If we have acid, we ain't doing E2. Okay, another way to dehydrate an alcohol is using pocylpyridine. Particularly good for primary alcohols because strong acid is not good to dehydrate a primary alcohol. Because it can be very tough to form a primary cation, carbocation. All right? What's better is to use pocylpyridine. Now, sort of similar to thionyl chloride with the SO, Cl2, like this. Okay, very similar. Reacts here first. We're going to move these electrons up, yeah? I'm just going to call this the R group. Okay, we're going to have phosphate electrons up, becomes O minus. All right, we have 3 chlorines. Now the oxygen with the butyl or whatever that is, dental group. We don't lose an H. All right, we do nucleophilic addition. We move the pi bond away from the phosphorus, not the sigma bond. All right, the second or third time we've done that. We will do it 1,000,000 times this semester, particularly when we get to carbonyl chemistry. Now the proton, we have to always take care of it. At this point, this H is now acidic. It's on a positive oxygen, just like the H on H3O plus is on a positive oxygen. Pyridine is a weak base, okay? At this point, previously I showed, we just left that proton there. Here, let's go ahead and take it. Either way works. These electrons take the H, and we can leave the electrons on the oxygen. That's going to give OR, and we make protonated pyridine. One of the main reasons I did this is because now we can ask, when these electrons here come back down, they're going to form pi bond here. Because we have something we can kick off, and anytime you can make pi bond, you kick off a leaving group. It's going to be easy and fast. Okay? When this comes down, what's the better leaving group, a chlorine or the OR? Chlorine, just like SN2. What's better? Chlorine can leave. Oxygens can't leave unless you protonate them. Back up here, which is a better leaving group, chlorine or protonated oxygen? Not as clear, is it? Perhaps the protonated oxygen. Or we can say equally. But by removing the proton, now we have a clear choice and say, hey, I'm going to do this because at this point, the best leaving group is obviously one of the chlorines. And when I reform the pi bond, I now have instead of doing R here, I'm going to have to now bring in carbons. Pencil. Yeah? We get to this point. That's just a substitution. We did an addition. Well, the addition was here. Then we took care of the proton. Then we did the elimination. Overall, it's a substitution. The chlorine used to be under my hand, but now the oxygen's under my hand. This is called a dichlorophosphate ester. Plus, well, we did make Cl minus, but we also have pyridine. Because we have pyridine, and I'm going to wait for a question to come in a second, and hopefully it's asked. At this point, this is a good leaving group. A lot like a tosylate. Tosylate, oxygen bonded to the SO2, something. Oxygen bonded to all this, it will allow for this oxygen to leave without it being protonated. At this point, the pyridine we come in here and these electrons take the H, these electrons move in here, and these electrons get kicked off, and what does that give? It gives that product. It's just turned around, double bond on the end. Plus, what was the leaving group? Plus that leaving group. It leaves because it's very stable. You can draw resonance. You also have the chlorines withdrawing. And instead of eliminating by an E1, which that would have to be, this then eliminates by an E2. Concerted beta elimination. Pyridine acting as a base. Pyridine is not a strong base, but it's apparently strong enough to do E2. So in this reaction, the oxygen becomes activated as this dichlorophosphate ester, and the E2 elimination takes place. I can imagine 2 questions here at least. Questions? Question.
What makes the OR group a good leaving group there, but then when the chlorine left instead of that OR group, I'm saying why is it a good leaving group right there versus right there?
The OR did not leave over here. The O phosphorus, all that left. That was left. This is not. OR did not leave.
Okay. Gotcha.
What about the chlorine anion? How wouldn't that take an H from the, yeah.
Cl minus?
Yes, sir.
Is Cl minus a base?
No, sir. I mean,
No, simple question. Is Cl minus a base?
no, sir.
If Cl minus is a base, then HCl is not a strong acid. Because how does HCl exist? Like in water, this. If that was a base, why would it not come back this way? Cl minus is not a good base. Okay? Because it's an anion. All right. Anions are conjugate of strong acids. Conjugate bases of strong acids are not good bases. If so, then what you're saying is you can do an E2 elimination with sodium chloride. No. If you can do it with sodium chloride, that means you don't need a base, because sodium chloride is not a base. All right? I thought you were going to ask this. Why does Cl minus, which is floating around, why does Cl minus not attack here and give you a substitution and make you an alkyl chloride? Just like cyanochloride reaction did. The difference is cyanochloride reaction doesn't include pyridine. And the only chemistry that can take place is the chloride, which ain't going to do elimination. It's not going to act as a base, but it will act as a nucleophile, and you get a substitution with cyanochloride. This goes E2 because you have pyridine there. All right? Now, some books will leave out the pyridine and just say, hey, guess what? Here it goes E2, and it's not. And you're like, why? Any other questions? Is there nobody wondering why we used pyridine twice, and how did that happen?
Is it just like, that's how I was wondering.
Because here, this nitrogen became protonated, but all of a sudden it's no longer protonated. Anybody? Anybody notice that?
Is it like a double equivalence?
Present in there.
Yes, this is going to require 2 equivalents of pyridine. 1 pyridine to take the H that becomes acidic. Then another equivalent of pyridine to do the elimination part. Usually you just use kind of excess pyridine. But stoichiometrically you need at least 2 equivalents. All right, so you can dehydrate an alcohol essentially by an E2. It's a mixture, okay? It's really not the alcohol that's being dehydrated, it's the phosphate ester, or the dichlorophosphate ester, which is formed in situ, meaning in the reaction. Paclopyridine. What does paclopyridine do to alcohols? Dehydration. There you go. No card. Question?
So pyridine isn't an sp3 nitrogen, so is it still a strong base?
As I said, it's borderline. It's borderline. And somebody might even argue with the mechanism I'm presenting here. Yeah. Question?
If the pyridine is present to like force it to go the E2 elimination mechanism route, then why do you need heat as well?
Well, you need heat for a lot of reactions.
Okay.
The heat requires elimination. That doesn't mean the other doesn't require heat. You may do one at 100 degrees Celsius, which is heating, and it may do like SN2 or something, 100 degrees. But if you do it at 160 degrees, then maybe it starts going elimination. And you say, well, heat favors elimination. More heat favors elimination. It doesn't mean that you have to do everything else at room temperature. Many reactions require heat. So this is getting more specific. More heat favors elimination. That can be going from room temperature to heating, or it could be going from heating to more heat. Okay, we've seen 2 or 3 times now using these thionyl chloride, this pacl, these type of reagents here. In general, that's a little bit something new we're seeing here. We're also seeing the addition elimination reaction as a overall substitution mechanism. Also, we're seeing we're going to take care of the proton along the way in many of our mechanisms moving forward. Okay, essentially this is an E2 elimination. And E2 has a stereochemical requirement, right? Anti-coplanar, anti-periplanar. Beta hydrogen and the leaving group must be, well, they must be coplanar. Preferred being anti-coplanar. Can you do a syn-coplanar elimination? Have you ever done one? You actually have, haven't you? Yes. Sound familiar? Okay. So give these a try and think about that stereochemical requirement. All right. Let's move down to O-alkylation of alcohol. Synthesis of ethers. Again, review. Good amount of review. Most common way to make the ether is Williamson ether synthesis. That is coming from the alcohol, generating the anion, and then doing an SN2 substitution to put the alkyl group on the oxygen. We first have to generate the anion. Okay, guys, you got to look at this and see here that this is what? First off, the oxygen-sodium bond is not covalent, right? That's ionic. Just like if we showed a sodium next to a chlorine, you know, that's ionic. This is just a sodium next to an oxygen. You got to look at this and say, okay, this oxygen is plus, that sodium, I'm saying minus, the sodium is plus, right? This is also organic chemistry, and I tell you what, group 1, group 2, well, that's not quite right. We will use magnesium soon. Sodium never does anything. I would basically get rid of this, and you got an anion here, right? That's what that is. That's the oxygen anion. How do we make oxygen anions from alcohols? One of the most common textbook ways is to react them with sodium metal. Okay? That is not sodium plus, that's sodium metal, oxidation state of 0. Very common way to make. This is the alcohol. What do you want to call this?
The
Alkoxide. Alkoxide, right? Alkoxide. Oxide is O minus. There's your O minus, but it has an alkyl group bonded to it as well. Okay? Back with sodium. Now this is not a traditional acid-base reaction where you can show electron movement. It's a radical reaction. All right? It does generate, what's the fate of this H? It does generate hydrogen gas. We demoed this in lab, is that right? No? You can balance this if you want, okay? Where did the two H's come from? Obviously you have to have 2 alcohols. All right? Very common. Redox reaction. We showed that in organic 1. There's another way to generate the alkoxides, and I didn't show it in organic 1, I don't think. May have seen it in another class. Let's react with sodium hydride. What's the charge of the hydrogen here? There's 2 clues to tell you the charge. It's negative. How do you know?
Sodium is always positive.
Our sodium is always plus, thus H must be minus. And I call it hydride. I is anion typically. Not always, but typically, yes. This is H minus. Okay? And to be minus, it's going to have 2 electrons. Not just 1, but it needs to have an extra 2. It's hydrogen with a lone pair, okay? It's hydride. It is possible. All right? Did we see this in organic 1 with me? Perhaps? I don't think we used it for this purpose. We saw it with like sodium borohydride, the hydride source. Okay? Now this is a typical acid-base reaction. I'm going to show a covalent bond because if we're going to do a mechanism, we need to have bonds shown. And here, these electrons can take the H, and these move on to oxygen. And what does that arrow movement give? It gives what I showed. Because the sodium cation is going to sit with the minus oxygen, right? And we made hydrogen gas right here. So that's a traditional acid-base reaction. An alternative way to make alkoxides. Now, once we make our alkoxide, what's the purpose of making the alkoxide? Okay. What does sodium do to the alcohol? Two-step reaction? That makes the alkoxide, right? Can I just do that? That's the result of the sodium reaction. Now we put in this benzyl chloride compound. What type of chemistry can take place? All right. Bam. Yeah? What else could take place? Anything else? Because as we go further, you're going to have to assess, okay, I know maybe 10 reactions. What's going to take place here? What's the reactivity here? And that's going to give what? Boom, boom, boom. Get that product there. Right? We just made that bond right there. And if you want to completely balance this entire process, what else did we form here? Sodium chloride plus what? Hydrogen gas. We formed that after step 1. Sodium chloride was not formed until after step 2. Did we get the stereochemistry right of the product? We just did an SN2, which comes with inversion. Did we get the stereochemistry right? Yeah? Yeah, that's right. Any questions about stereochemistry? Why is it right?
The chlorine's already in the plane, so you don't have to use it. Or
Well, the only stereochemistry we have here is right here. Why is that right?
that's not what's being attacked. That part of it.
Because we didn't do any chemistry at this carbon. There should be no change. Okay? Right? What about this product?
You have two things in the plane. Sometimes
What about that product? Would that be formed? Would that be formed? Who says yes? Who says no? Who's not voting? Well, the answer is yes, because that's the same as that over there, right? Same thing? not?
You show.
Are those the same thing? I think they're the same thing. I just drew it a little bit different. Same thing. That's the same thing. It's got the same connectivity and the same stereochemistry. If you named it, it would have the same exact name, including stereochemistry.
But the dash line is the same stereochemistry that's over there?
Well, this carbon is S, correct? Isn't that S?
Yeah.
That's S here as well, correct? Right?
Yeah.
And the connectivity is the same, right? It's an oxygen with a benzyl group, and the oxygen is bonded to a carbon, which has a methyl and an ethyl. I had to look at it. It's the same compound. I just turned it around. The answer is yes. This is your product. There's only one product on the board. It's the same thing. Just like, look at my hand. All right? Now look at it. How many different hands did I hold it? There's one. There's the other. How many different hands? It's one hand. I'm just showing you. Okay, how about now? That's not a third hand. It's the same hand. I'm just showing you. How about now? One hand. All right? Okay, let's move on. Phenols are more acidic, right? Phenols are more acidic because of resonance. The anion here, get rid of that. The anion here is resonance stabilized, right? You can show resonance structures. The charge is delocalized. Because of that, we can deprotonate phenols using hydroxide, which is a much more common and simpler base. You cannot deprotonate regular alcohols with hydroxide. All right? But phenols have a pKa more like about 8 to 10. It's a standard acid-base reaction. Hydroxide takes the H, you make the phenoxide, phenoxide plus water, for that's pKa of 16, which is favored, 10 or 16. Weaker acid, this side's favored. It's favored by 10 to the 6 at least. That's enough. It's very favorable. Okay? You can make phenoxides using a much more common and weaker and safer base. Something like sodium can start a fire. Did we start a fire last semester? We didn't. We started a little fire with sodium. And how much sodium did we use? That much? Imagine using more like a, and then getting that around some type of wet solvent or the wrong solvent. Hydroxide's not probably going to start a fire. I think it could, but very unlikely. Product here. All right. Well, you can do this on your own. We'll look at it. Okay. What's KOH going to do? What's the difference between sodium hydroxide and potassium hydroxide? Not a thing for us. Now, in practice, there actually is. Because in practice, KOH is more soluble in organics than sodium hydroxide. When we did the double E2 elimination, we used KOH. We're using an organic solvent. And the bigger the cation, if you go down potassium, the bigger the cation, the more soluble it is in organics. Like cesium. Cesium carbonate is very common because it's more soluble in organic. Now, if you're using water, they're all the same. So they're all going to dissolve in water. Lithium hydroxide can sometimes be a little less basic because lithium is so Lewis acidic. So there are some practical differences. But in general, there's, the opening comment, there's no difference. I mean, for us, it's hydroxide. What do we have here? Carbon with a leaving group? Okay. I mean, we assess what we have. Okay, let's do synthesis. Synthesis, we're going to be going backwards. How would you synthesize this compound if I know the name of this compound? It's actually MTBE. Used to be used as a gasoline additive, methyl terbutyl ether. Somebody doesn't know how to do nomenclature, but, okay? How would you synthesize that compound? It's an ether. Everybody agree it's an ether? What's the most common way to make ethers? Williamson ether synthesis, which comes from, you have alcohol and you alkylate it. All right? What alcohol would you use here? Because we have choice. We can go backwards. This is called retrosynthetic analysis. Let's do a little retrosynthetic analysis. All right? That sounds fun. I could go back to maybe this oxygen nucleophile. Let's call this A. Let's make that oxygen carbon bond. And react that with what? Maybe something like that? The carbon with a leaving group? Now let's go forward. Will these two react to give that? This looks naked here. I'm going to put an ME here. That's okay. Just one line. Are those two going to react? So is our let's analyze our suggestion here. Is this a good reaction? Is that going to give the product? Yes?
Yes.
You're saying no. Why not?
That's the
Does it have
SN1.
to,
Should be pretty straightforward, guys.
Has to be SN1.
bromine is on the front part?
Bromine is where?
Oh, never mind, it's on the tertiary.
Well, I think you said it. This reaction is no good. Leaving groups on tertiary carbon, you never do SN2 on tertiary carbon, right? What's going to happen here instead, most likely? If you've got a strong nucleophile slash base, what's going to happen here instead? This is likely going to give E2. And E2 is going to give an alkene. I mean, that will not give. We want an SN2. You don't do SN2 with leaving groups on tertiary. It's not a good reaction. So let's consider making the other bond, B. That would be taking this alkoxide and reacting it with something like methyl iodide. Which, when you're using methyl, just methyl, usually you want to have the iodide, methyl iodide. Those methyl bromide's a gas. Methyl bromide's a liquid and thus much more commonly used. Okay, well this reaction give that. All right, sometime, if we're going to, I can change this to CH3, still methyl iodide. We can say this is going to appear and kick that off. Is that reasonable?
Yes.
It's very reasonable. We're doing an SN2, the leaving group's on not even a primary carbon, it's just a methyl. Very easy SN2. Yes, SN2. There's your reaction we're going to propose. We see that after doing a little bit of retrosynthetic analysis. You may have to start with only neutral compounds or something. How would you make this alkoxide? Well, this comes from what? Comes from alcohol. I mean, that's pretty straightforward. Back that up to the alcohol. And then coming forward, how would you do the reaction?
NaH or just NaH.
Uh-huh. Sodium metal. Or potassium, okay? Because guess what? Potassium also works. The only reason I point that is because with tertiary alcohols, that is a tertiary alcohol, right? With tertiary alcohols, potassium is more common. That's just a little free information. But you know, I mean, if sodium does this, you would expect maybe potassium to do it too. Similar group properties. Okay, you can try one on your own. We'll do that next question.
So does that mean KH works just as well as NH?
Well, potassium hydride is known, and it's not as common as sodium hydride. And, well, and potassium is not as common to be found in the lab as sodium either. I think I've occasionally seen KH used. Yeah. Actually, the potassium versions are going to be more reactive. Because they're even less electronegative. They're more electropositive. Because the trend goes, fluorine is the most electronegative, and then way down over here would be the least electronegative. And they're the most eager to give up electrons. That's more relevant for the metals rather than the hydrides. And so we put sodium, generated a little fire in the sink last semester. Potassium, you got to watch out. I was cutting the sodium just kind of open. With potassium, you try to cut it open, it may just ignite right there because there's enough moisture in the atmosphere. And potassium is very reactive compared to sodium. So you got to be much more careful handling potassium, and then just handling cesium is like, okay, you just open that up, it's going to probably ignite. Because there's vapor in the atmosphere. Okay. Need to be able to do that, finish it up, think about the questions down there. We'll look at those. And we're ready to look at reactions of ethers. Okay? Green sheet. We did some substitution, mainly replacing the OH with halogen. We did some elimination. We just did O-alkylation. We used some ether synthesis, making ethers. We will do oxidation a little bit later. At this point, though, let's move to chemistry below, chemistry of ethers and epoxides. Now, ethers tend to be end products. Okay? You can't do much chemistry with an ether. That is, kind of keep going. And that'll make more sense when we say that a common reaction of ethers is actually to break them apart, to cleave them. And when you cleave them, it's almost like doing the opposite of a Williamson ether synthesis. Williamson ether starts with an alcohol, and you eventually convert it to the alkoxide, but then you react with an alkyl halide and you get the ether. But when you cleave ethers, you get an alkyl halide and an alcohol back, kind of. Let's see how this is done. This is our friend MTBE. If you take it and react it with HBr, you can get some chemistry. So what could happen here? Tell me first step, mechanistically, what might happen first?
You have to hydrogen to protonate.
We've got a strong acid, HBr. Very often when you are doing a reaction under acidic conditions, you want to protonate something first. Well, the only thing we can protonate is the oxygen. Okay? These electrons here, protonate. Now what can we do? we got a BR minus. Can anybody propose the next reaction? What can happen next?
Oxygen base.
Or the,
And let me just clarify, okay? Hopefully you've kind of seen this, but maybe not. The more and more we move ahead, we're going to rely on things we've seen before. We've covered many of the basic principles, okay?
go SN1.
Protonation, PR minus, what could we do? These are questions that you should be thinking, okay, what have we done in the past? How can we do the same types of things and just call it an ether cleavage now? What could be next, somebody?
The alcohol leaves.
Bromine could attack the carbon and kick off alcohol with the methyl.
Okay, a positive oxygen can be a leading group for like SN2 and substitution elimination, right? We got a positive oxygen now. You said attack carbon. Which carbon?
The tertiary carbon.
By what type of mechanism? Because you don't do backside attack on tertiary carbons, right?
So it'd be SN1.
That's a one.
One option is we could do an SN1, which is leaving group leaving. Is that reasonable?
Yes.
Could we just show this leaving and make a tertiary carbocation? Yeah. But how about this? What if bromine attacked this carbon and kicked that oxygen off in an SN2?
That could work too.
That's also reasonable. Here's what we have. We have choice. You got a carbon on either side. Okay, here's kind of a rule for this type of reaction. We'll see this kind of again with epoxide. When you have a tertiary reaction site present, always go SN1. If no tertiary site is present, go SN2. Okay. We have a choice. Do we have a tertiary site present here? Yes, right here. Thus, we're going to do what? SN1. Thus, the leaving group is going to leave. Which carbons are going to leave from? This one. We're going to do this. Leaving group's going to leave, and we're going to get this carbocation plus what just left? Methanol. Methyl OH. Methanol. Okay? That's the leaving group that just left. That's the alcohol. And first step of SN1 is leaving group leaving. How can we finish this up? What could be the next? BR minus coming around. And this attacks here. And we end up with that. And those are your two products from this ether cleavage. We're actually getting back an alcohol and an alkyl halide. When you cleave with HX, and it's a common reaction, HBr or HI or HCl. Cleavage of ethers using HX. Other than that, ethers are pretty unreactive. They tend to be end products. We'll talk more about them. Dealkylation. Look at this. Here the oxygen has two alkyl groups. One's a terbutyl, one's a methyl. Everybody agree? Now the oxygen only has one alkyl group, just the methyl. Does everybody agree that we have dealkylated the oxygen?
Yes.
Okay? So if you want to focus in on that, we can call it a dealkylation reaction. What about the next reaction? What would be the products there?
You want it to attack the methyl because it's more more acetate.
Okay, and we'll pick up here on Monday. We'll have our first quiz next week. Question is, do we have a tertiary site here? So what does the rule tell us? Read the rule, do the reaction, see what you get. Okay, we'll look at it on Monday. Have a good weekend, guys. See some of you upstairs. Begin at 2:30.